Radio telephony, HF communications, uses amplitude modulation. We also use it for our signaling in the trunking system. Signaling. Uses a type of keying called amplitude shift keying. And we use it in the microwave, point-to-point digital microwave system. Okay.
I have a question also related to this.
Yes. How does this work?
You change the carrier
Frequency, according to the amplitude of the modulating signal. Probably the easiest way to show this.
Frequency deviation.
Yes, that's right, the deviation. The easiest way to show frequency modulation is not to choose a waveform like that, it's a little bit complicated. It's to choose a spectrum here, where this is our carrier. Right? Now, if I was to amplitude modulate that carrier, I produce two sidebands, don't I? Remember?
Yes.
Well, what we do with frequency modulation, I cause the carrier to increase and decrease in its frequency according to the amplitude of our modulating signal. For example, if what I'm drawing here in green is my modulating signal, then it causes the carrier to increase, decrease, increase and decrease according to the amplitude of the signal. Right. One half cycle, the other half cycle. So the frequency of the carrier is changing, not its amplitude. If you were to draw it on a waveform like this, it's a little more difficult.
spring compressor on the side.
Yes, you begin with a carrier. Let's just a couple of lines in here to see. There's our carrier. And then you increase its frequency, you see what's happening? And then you decrease its frequency. And then go back to normal again. So that's an increase in frequency and a decrease in frequency from the carrier. Notice the amplitude of the carrier is same, yes, that's not changing. The amplitude doesn't change, the frequency changes. Frequency modulation. Okay? Very simple principle, FM, as we call it. A little more complicated to decide on sidebands. Obviously, the way the frequency changes, the more we change it, the wider is going to be the bandwidth. But it's not just a case of maximum and minimum carrier frequency. Because of the way the FM signal works, additional side frequencies are generated. And in theory, and it's just in theory, an infinite number of side frequencies are generated, which get smaller and smaller the further away they get from the carrier. In practice, we don't allow these other frequencies to be transmitted. We use, again, in the transmitter, some type of bandpass filter, which selects only the carrier, right, and just perhaps one or two side frequencies, which is sufficient to contain the information. But one important thing about FM, for a given amount of modulation, the bandwidth is always wider than it is in AM. So the thing I want you to remember is the transmitted bandwidth is wider than using AM. It's to do with these side frequencies that are generated when you frequency modulate a signal. Although we don't transmit all the side frequencies, we do need to include some of them, otherwise the signal gets distorted. And the result is a wider bandwidth to be transmitted in order to maintain the information. Now this would seem to be quite a big disadvantage really compared to AM, a wider bandwidth. Remember, one of the objectives is really to try and keep our bandwidth as narrow as possible so we don't interfere with people. But there are some other advantages using frequency modulation.
There is no cutoff. I'm sorry if you know the amplitude modulation criteria, it depends on the amplitude signal.
Yeah. Oh yeah, if you overmodulate, you're talking about. Yeah, that's true. But of course, again here, the more you modulate, the more frequencies you're going to generate. So you would end up distorting the signal anyway if you overmodulate, yeah, but maybe not to the same extent as you would if you cut off on a carrier. Yeah, so we have a disadvantage with FM here, and yet we should probably be aware in radio that FM is quite common,
Yes.
particularly in radio telephony, isn't it?
Yes.
So why do we use it, do you think?
Depends on the force, frequency of the
You
force.
can transmit higher frequencies
Not at the same
than
time.
the can transmit much more bigger bandwidth.
Than AM?
In AM, you transmit from 300 hertz to 3K hertz.
Ah, well, that was only an example. That was only an example. I mean, I could have chosen a bigger bandwidth if I've
If
any.
you choose a bigger bandwidth, it should be you need a very big, a high power transmitter and a high frequency.
Well, that might be true, but just regarding bandwidth alone, let me just say that what we've got to do is compare light with light. If I'm talking about a telephone circuit with, say, a 3.5K bandwidth, I use AM, it will take less bandwidth than using FM.
Yes.
Now, of course, if I choose a different example, let's say a radio broadcast, which transmits not only speech but also music, that might have a 10 kilohertz bandwidth.
Yeah, you need a bigger bandwidth in an FM.
Yeah, well, you still need a bigger bandwidth in FM than you would in AM.
Yes, we
Yeah,
need
because you get a lot of tunes
Yes.
with a high frequency
Yes.
that can't be transmitted in the AM.
Oh, they can be transmitted on AM. They can.
You need a bigger band.
But so with this. The higher the
That's why you
modulating
got
frequency, the
by
higher
nature.
the greater the bandwidth needed. Now, this is the reason why I'm asking this is because, again, people tend to get confused between FM and VHF. For instance, remember the two bands we talked about? We talked about medium frequency band and VHF. Well, we have HF as well, of course, in between, and VHF. What was the FM band? Let's just quickly put this down, remember?
300
300
Kilohertz.
3K.
To 3 megahertz,
3 mega to 30.
3 megahertz,
To 30.
to 30 megahertz,
30 to 300.
and 30 megahertz to 300 megahertz. Now let me just tell you first of all that FM frequency modulation is mainly used, if we consider just these three, out of these three bands it would be used here. Whereas in these two bands the modulation would probably be AM. Now the next question is why? And this is the point I'm trying to make here. Why would they use FM here? Why don't they use FM here or FM here?
There's a high frequency.
More
in the
bandwidth than, yeah.
Yeah, there's a bigger bandwidth with an FM signal than there is with an AM signal
Yes.
for a given type of modulation. And that's the reason why we do not use FM in either of these two bands, because there isn't enough room. Right? Here we've only got from 300 to 3 megahertz, 300 kilohertz to 3,000 kilohertz. There isn't enough room for FM signals. It's the same with the HF. There's not enough room for everybody to transmit in the HF band using FM, using frequency modulation.
Again.
What I'm saying is, the bandwidth, you must, remember what we said here, and I've only made one point. One point was the bandwidth of an FM signal is wider than an AM signal for a given modulation, for a given type of signal.
Because this is limited. VHS is
Yes, that's right. Whereas VHF, we've got a greater amount of space for more channels, haven't we?
Yes.
So we can use wider channels.
Yes.
Whereas here we don't.
Also, you chip it on a different.
And also,
You chip.
yes, UHF, we could use FM as well, of course. Higher frequencies, that's true.
So that
But
is-
just comparing these three, this would be the only one that we would be able to use FM.
We have. You mean we have more space
More space?
to get wide band within it.
Exactly. Now the next question, and this brings us back to why we use FM. Why do we bother using FM if it has a wider bandwidth than AM?
And information.
Someone takes said lot of information what to send.
So
Why do you use FM more than the AM?
No, why would we use FM at all? For example, let me just give you an example. Let's say I've got a signal which goes from, say, 1 kilohertz to 100 kilohertz. That's my signal.
Yes.
Very good signal. More than we would normally need for audio. However, there's our signal. Now, if it was an AM transmission, let's say it was single sideband AM without a carrier, then what's the bandwidth?
Without the carrier?
Yes, without a carrier, 99 kilohertz. Now, with FM, we'll find that our bandwidth is going to be at least 3 times this, at least 3 times that, up to a maximum of about 300 kilohertz for the same signal. For the same signal.
So annoying.
It's not narrower than this, it's wider than this. Okay? So this is a disadvantage that I've mentioned here.
Yes.
I haven't mentioned any advantage. I've not mentioned any advantage, so why bother using it?
As you said, the higher information.
Noise, this is it. It's not the high, the information's there. The information is there, here, and here. All the information's there. It's to do with noise. The whole point about using FM is signal to noise ratio. Remember, noise is electrical signals, isn't it? That are in addition to the signals we want. Signals we don't want. And usually, most noise is amplitude noise.
So why we use AM?
Wait a minute. Amplitude noise. So a noise in a system is usually changes or small changes in amplitude. Now, if I have a carrier, okay, I can either
Disadvantage or advantage for FM?
just everybody just listen to what I'm saying, because I'm going to repeat this once. If I have a carrier, okay, there are 2 ways in which I can modulate it. I can either amplitude modulate it, or I can frequency modulate it. Okay? Now just forget about bandwidth for a moment. By the time that carrier is received at the receiver and amplified by the receiver, we get noise on it. Can't avoid that. Noise is going to be introduced. This is just natural, isn't it?
Yes.
Now most of the noise is going to occur as small changes in amplitude. Maybe big changes in amplitude, depending on the type of noise that we're going to get. Now, if I'm using amplitude modulation, these small changes in amplitude are going to be demodulated the same as the signal and produce noise at the output.
Yes.
But if I'm using frequency modulation, then my receiver is designed to look at changes in frequency, not changes in amplitude. It ignores changes in amplitude. Changes in amplitude don't mean anything to an FM receiver. So my FM receiver only detects the changes in frequency. It ignores the changes in amplitude. So the output from my speaker will be very clear with no noise. So the signal to noise ratio of an FM system is much better than an AM system. And that's the reason why we use FM. Not because of the bandwidth. The bandwidth is a bit of a disadvantage, the wider bandwidth. But it gives me a clearer signal. You know that, again, if you take radio broadcasts as an example, on the VHF band of your radio, most of your broadcasts are in FM, aren't they? They talk about FM, VHF more or less in the same breath. FM, why do they use FM? Low noise, much clearer signal, much higher fidelity, as they call it, compared to AM. Although the signal actually takes up a wider bandwidth. But that's the cost we pay for giving us a better signal. So in an FM system, let me just write this down, in an FM system, the advantage is a better signal to noise ratio. So this is a disadvantage, this. So, what's the advantage? And I'm only going to mention the two things. That's the disadvantage, but the advantage,
Noisy.
yeah, advantage is better signal to noise ratio. That's really the bottom line. And that's the reason why FM is used.
What about disadvantage? Can you write it, please?
This,
This one?
yes. Transmitted bandwidth is wider than using AM. If we're comparing the two, comparing AM with FM, I'm comparing the two when I'm talking about the advantages and disadvantages. The transmitted bandwidth is wider than using AM. That's the disadvantage. But the advantage, better signal to noise ratio.
So the AM has noise. Why we don't use it? Why we cancel it?
Why do we use AM?
Yes.
We use AM on frequency bands where there isn't sufficient room for FM. It would be nice to use FM all the time because of the high signal to noise ratio. But look, let's say an FM signal takes up 300 kilohertz. Look at this MF band here, which goes from 300 kilohertz to 3,000 kilohertz. There isn't sufficient room there for channels. We can only get several channels in there and then it's full. We've got no room for anybody else. Right? So we have no choice. Here we've got to use narrowband transmissions. We've got to use AM. And here also we've got to use AM for the same reason. Because it gives us more channels, narrower band. But with FM, it's a wider band. Well, we can use it on VHF and we can use it on UHF, but we wouldn't use it on these two. Do you see the reason?
The FM has a wide bandwidth.
Yes.
Advantage, not disadvantage.
No.
Because more channel we can.
No. This is the bandwidth of a channel, of a single channel. When I say wide bandwidth, I'm talking about the bandwidth of one channel. Now, let's say I've got a certain band of frequencies. The bigger the bandwidth of any one channel, the fewer channels you can fit. If you use narrow bandwidths, then of course you can fit a lot of channels. Do you see the difference? Don't get the two confused. This bandwidth here refers to the bandwidth of the channel.
One channel.
Of one channel.
وايد bandwidth.
زي افتكرها
Noise
عدة
would be
channel.
less.
بس
There's no noise.
but هي مو مشكلة.
Well, here it is a frequency, as you said.
Well, the reason why there's no noise is because it's frequency modulation instead of amplitude modulation.
You said in the receiver.
Hmm.
The receiver
No
doesn't.
It ignores the amplitude and just looks at
The
it.
shape of the signal is only
Yes.
the signal.
A special detector is used just to detect these frequency changes. and that's what produces the output signal, say from the speaker.
Frequency, different frequency make high bandwidth.
Yeah, with frequency modulation, you're using a wider bandwidth for each channel. So that obviously in any given system you can only afford a few channels if you're going to use FM.
Because in the radio, so we hear it in the air, it's
Yeah, you compare, you tune your radio.
Yes, only 2 or 3 channel.
Yeah, but you tune a radio to AM signal.
AM.
This is on FM, on medium frequencies. On the medium frequency band, AM signal.
not clear.
It'll be more noisy.
Yeah.
You go to VHF and tune to an FM signal, it'll be more clear. You'll be able to hear it more clearly without noise.
Also, FM only 2 or 3 broadcasts.
Oh, I don't know about that. I'll tell you now, in the UK and in the United States, the FM is crowded with many, many stations. I'm not sure the bandwidth. I think the bandwidth is about... What's an FM bandwidth? 200 kilohertz? So you're not going to get many of those in a particular band, are you? That's the reason why they're restricted to VHF. Rather than these... You wouldn't see FM broadcasts on these bands.
Almost constant 75.
كده 5 أقواس
Sorry, what was your question again? The deviation. I haven't mentioned deviation, but go on. What was your question?
Maximum 75.
It depends on the system what the deviation is. The deviation, by the way, for those who want to know, is how much the frequency changes for a maximum signal amplitude, isn't it? From the carrier. And there are different deviations. The greater the deviation, the wider is going to be the bandwidth that you transmit, that's for sure. In our FM systems, what's the deviation of the trunking radio system? You wouldn't know this one, so you might know. What's the deviation of the trunking radio system? Can you remember? Gone out of your mind. It can be 50 kilohertz or 75 kilohertz are common values, aren't they? 50 or 75. I'm not quite sure which one it is. These are typical values. Will it give you your mobile radio is FM?
Yes.
Using UHF. If we take the trunking radio as an example, the walkie-talkies and the car radios, they're all FM. At the moment. Mainly because there's no room in the VHF bands.
That's the reason, but simple building is very...
I know, that's true. If we had enough sufficient space in the VHF band, it would be an advantage. Because as you say, you get better coverage, go through the buildings. But it works.
But why is it what they said when you're on the plane, turn off your mobile? There's no
Are you talking about on the plane? You're talking about GSM? Yeah, you're talking about cellular radios. There is reports of interference with the navigation systems and the electronics on a plane. Not only from the radios, but also from computers, laptop computers and things like that. You're using anything that can radiate electromagnetic energy, even if it's a very small amount.
Any frequency.
Is the root of, right, this squared plus this squared. Now, if these two are equal, then it's equal to the root of 2 times, well, it doesn't matter, VR or VC, because they're both the same. The root of 2 times this. All right. If you wanted to know what the power of the output is compared to the power of the input, all right, this is the input, the output is VC. So this is input, VC is output. In other words, I'm taking the voltage from across the capacitor. Actually, it doesn't matter which you take, as they're both equal, but in this case, because it's a low-pass filter, I'm taking the voltage across the capacitor. If you take the ratio of these two, it'll give you output over input. All right? And if you take the ratio of these two, you end up with root 2 as being the output over input, root 2. Output voltage over input voltage. What is power proportional to? V squared. Does it not? V squared, power, V squared times R. Yes, output over input, right, is the ratio of VC to root 2 times VR. Do you agree with that? Root 2 times VR. Just put root 2 times VR there. It means the same thing. Therefore, the ratio of output over input, we can say V output over V input, is equal to VC divided by root 2 times VR. Now, VR and VC are the same,
Yes.
isn't it? So in other words, the output over input is 1 over
Take the R out.
root 2. Sorry?
Take the R out.
Well, what I'm saying is, in my example, and it is just in this example, if XC is equal to R, then VC and VR are equal. Agreed? So I could put here VR or VC, it doesn't matter which one I use. Right. Now the ratio of output over input, I can take as my output here, in this case is VC. So VC divided by this, if this is my input.
How could you take square root of 2? How do you take only the square root of 2 out and the VR out?
I did it by changing this formula to this. Right. This is 2 times VR, isn't it? Squared. Yes. In other words, yeah. VC, it doesn't matter, these two are both the same value anyway, VR, so it's 2 times VC or 2 times VR squared. And then rooted, well, the root of VR is VR, and the root of 2 is root 2. So just keeping it as root 2. Hence, the ratio between the two is this.
1.4.
Yeah, this is 1 over root 2, or 0.707.
This is the gain.
This is the ratio of voltage between the output voltage and the input voltage. Okay? The ratio of voltage. All right? So when XC is equal to R, the output voltage, V output, from my filter, is equal to the ratio of 1 over root 2
0.7.
times the input, which is 0.707. Okay? But if I wanted to know what this is as a power ratio, I have to take the square of this, because the power is proportional to the square of the voltage. So as a power ratio, the ratio, what is 1 over root 2 squared? Yeah, 1 over root 2 squared is 1 over 2, isn't it?
1 over 2.
Yeah, 0.5. The square of this is this.
Yes.
So it's 1 over 2. So in other words, the output power is half the input power. Okay? We call that the half power point. And if you remember your decibels, in dBs, what does half power mean?
Attenuation.
It is attenuation, so it's a negative number. Remember, multiplied by 2, it's 3 dBs.
Yes.
So we're dividing by 2, minus 3 dBs. So we call that frequency the half power frequency, or the minus 3 dB frequency. Now let me just erase this and put the results of this on this side.
other way,
There's 2 or 3 ways you can do this.
we did it in the last week, I think, for people by X.
Well, I haven't changed that. I've said if XC equals R.
Yes, they are.
That's all I've said.
Yes.
Now we can see how the frequency is going to be affected by this. In other words, if I gave you the value of R and gave you the value of
Change of
C, then you should be able to find out what frequency the half power frequency is for this. And this is a standard way of measuring, this is what we call, it's a standard way of measuring the cutoff frequency. Oh, not cutoff point, this is the cutoff point. If I was to draw a graph of this, remember that this is a low-pass filter, so we're going to get a graph something like this. Okay, this is our low-pass filter, where the output is plotted against frequency. At a certain frequency, the output power is half the input power. So we call this the half power point, or the minus 3 dB point, means the same thing. And that's when XC is equal to R. Okay?
cutoff point.
It's called a cutoff point. Now, it's not very clear as to why that's cut off, but what they're saying is, okay, it's a point in our graph. We say anything above that frequency, the signal is rejected. Anything below that frequency, the frequency or signal is accepted. I used these 2 words last week, didn't I, or the week before last, to describe the cutoff frequency.
Plus here, slow pass filter.
It's a low-pass filter.
Yeah.
These are low frequencies, these are high frequencies. So we say that we get a better output power at lower frequencies and lower output power at higher frequencies. So another way of mentioning this is what we mentioned the other week, is we say that these have been rejected and this has been accepted. I used those 2 words, I think, when I mentioned this last week, when we were talking about filters.
Then we can see here, if it's lower than minus 3 dB,
Then it's say it's rejected.
then the voltage rejected, the signal rejected.
Yes, that's what we say.
This is higher than...
It's been accepted. Now this is just a standard level that's been, you know, universally agreed as to be the point, what we call the half power point of our filter. And in this example I've shown here, I'm choosing a low-pass filter. If I was to choose a high-pass filter, we would use exactly the same math. There'd be no difference in the way we calculate, except these would be the opposite way around, wouldn't they? In a high-pass filter, if it was a high-pass filter, it's just that we use capacitor here and resistor here. That's right, this is our input, this is our output. But we assume exactly the same calculation. Here there's no difference. XC is equal to R, and if XC is equal to R, then that's where our cutoff frequency is. Now I think we actually did a calculation, didn't we, at the end of the electronics?
But the difference will be in accepted and rejected.
Yes, that's right. The difference would be the slope would be the other way around here. The lower frequencies will be rejected, the higher frequencies will be accepted. But we can always calculate, if necessary, what the cutoff frequency is, simply by knowing what the value of C and R is. The cutoff frequency is when XC is equal to R, so
No, we must know the value of C.
that's right, you do need to know it. So what we're saying is 1 over 2 pi fc is equal to R. And what I want to find out is F, the cutoff frequency. So F is equal to 1 over By R.
CR.
CR, yes, that's right. If you needed to calculate that, I'm sure we did one like that. But the point I'm trying to make here is that we have three names to describe this frequency. One is called the cutoff frequency. The other is called the minus 3 dB.
Minus 3 dB is the cutoff point.
That's right, the cutoff point or cutoff frequency. And the other one is half power. These three names can mean the same thing. You could, I've noticed in test questions they can use any one of those three names to describe that frequency at that point on the curve.
That we said resonant?
No, I've not mentioned resonance yet.
Not resonant.
No.
This is just a
This is just a filter, simple filter,
cutoff frequency.
a cutoff frequency, yes.
Simple President's formula, V S squared to power to 2 equal power to
This one,
yeah.
this is to show how we call it the half power frequency. You get half the output power when X equals R. That's really what this proves. You won't have to prove this in the test, by the way. This is just for your sake, just to complete, to make sure you got everything there if you wanted to prove to yourself. When VR is equal to VC, okay, then the relationship between the two of them, which is our source, depends on root 2.
Like we were finding the RMS.
Well, I'm assuming the current and voltages we're talking about here are all RMS.
Find the RMS from the
Yeah, but it's like that,
light, right? Yeah.
but, it's not, we're not actually involving ourselves here with RMS. I'm just assuming it is all RMS values.
Then it's recording the call it half power.
Yeah, three names, half power.
Half
Yeah.
power.
I thought I'd given you this before, did I not? Or did I? Anyway, let me put it down just in case I haven't. So that you've got it down anyway. Yes, for a simple filter, that's true. Over 2 pi CR. CR that is. No, CR. So cut off. Frequency at which the output power is equal to half input. That's essentially what we're talking about here. Three ways of describing the same thing.
Same thing.
When the output power is half the input power, that's called the half power frequency. And it doesn't matter what type of filter actually, and as we'll see later, even in tuned circuits we can talk about half power frequencies.
Frequency at right?
Which
At which the output power equals half input power.
I'm talking about voltage now or power?
Power.
Power ratio.
Yes, that's right. That's why we can use decibels. It's the square. It's the square of this, you see. So it becomes 1/2. We're using the square of the voltage.
يعني كده نفسها يعني The same thing means that.
All of those mean the same. In a test, you might find any one of those three things, and you've just got to remember that they all mean the same thing. Cut-off frequency, half-power frequency, minus 3 dB
When you
frequency.
say the high power frequency would be 3D frequency or
The high-power,
frequency. The high pass filter
high-pass filter,
would be 3 dB frequency.
well, it doesn't matter what type of filter, whether it's high-pass or low-pass, you can still talk about the 3 dB frequency.
Still minus 3 dB.
Yes, always minus 3
High
dB.
or
Doesn't matter whether it's high-pass or low-pass.
the same.
The only difference, the only difference between high-pass and low-pass is, let me give you some examples of this. For instance, here, if we draw a high-pass filter, I can draw 3 examples of a high-pass filter. One like this. That's a high-pass filter, isn't it? One like this. And one like this. Right, there are 3 examples of a high-pass filter. All of them are high-pass, A, B, and C. However, they've all got one thing in common. They all use the same half-power frequency. If this is the half-power, this is power, right? Output compared to input. If that's the half-power point, they all have the same half-power frequency, which is this frequency here.
Cutoff.
The cutoff frequency. All of them are high-pass filters, A, B, and C, and they all use the same half-power point. The graph C would be one that's made from just a resistor and a capacitor. Graph B and A are more complex. We haven't done the sort of circuits, but they would be more complicated high-power, high-pass filters. If we do a low-pass filter, same thing, only the other way around. Again, we talk about the cutoff frequency. Only everything goes the other way around.
Muhammad Kareem, Aziz.
We can talk about the same thing.
Or the accepted
By now, of course, in the low-pass filter, the lower frequencies are accepted, and these are rejected. And here's the other way around. Here, they are accepted, those are rejected. There's the difference. Do you see that? Are they okay?
His 3 names is for the high pass filter or the low pass filter.
Yes.
Cutoff frequency or half power.
Doesn't matter what type of filter, we can still talk about these 3 things. They're all the same.
Maybe become a question. The test give you multiple choice and you circuit high pass filter.
Generally speaking, they're quite simple. There's very little calculation in the
No,
test.
they didn't ask you about this. What's the name of this?
Basically, what the name of the filter
They don't
is.
say high pass or low pass.
You just got to look at the circuit to see whether you think it's a high pass or low pass.
Okay, don't put it in the multiple choice high pass or low pass. They put it.
Oh yes, like last time they put an
Yes.
integrator or differentiator.
Yes.
Yes, you must understand that as well.
They put the name of them, of this 3 name, our cut off frequency.
They won't put all those 3 together on one
only
answer.
of them.
Yeah, one of
You
those.
Choose it.
Choose yes. If it points, if they might give you a graph,
Yes.
and they'll point to a point here and they'll say, what is this? Is it the cutoff frequency or something else? But they won't give these 3 choices because they're all the same. You won't get those 3 as the same, and as the same choice in a. You can give any one of these, but not all 3. We used to have questions in the test where they might give all 3,
I'll give you
and then
first.
they'll say all of them are correct. But we've tried to avoid those sort of questions now.
Is the point the cutoff frequency? The point.
Cutoff frequency, yes. This F here, an output is this. That's what we're talking about. Cut-off frequency, half power frequency, or minus 3 dB frequency. Okay, then that's great now. With a simple filter, then the half power frequency is when X equals R, or when XL equals R. A simple filter is one with just one resistor and one reactance. Okay, either a conductor or inductor or capacitor. These are all examples of simple filters. All examples of simple filters.
هو يكسر فيه بدل بدل يبدي فيه بدل هذا كل ضغطة 10
Problem? The mic is on there. Filters these are.
simple filter.
These are all examples of simple filters. A simple filter is basically a filter which just uses one reactance and one resistor. Simple filter. And as far as questions in any test is concerned, no matter how difficult the test, usually the filter is simple. If it needs you to work anything out, it'll be a simple filter. If it gives you anything more complicated, if it gives you a filter like this,
that we have in the paper that
now that's a more complicated filter, and the calculations involved with this are much more complex.
sometimes
But you should be able to tell whether that's a low pass or a high pass filter.
from see here from first.
Yes, just by looking at the design,
High pass filter.
it is a high pass filter, yes.
But we sometimes put inductor and capacitor.
Yes, now I'm going to mention that in a minute. I haven't talked about that yet. We're going to talk about inductors and capacitors together in a minute. For the moment, for instance, this one here, what type of filter?
Low pass filter.
Abdullah, what do you think?
No, bus.
Low pass, yes.
pass filter.
A low pass filter. And this one,
High pass filter.
high pass filter.
High pass filter.
Another high pass filter. And of course, low pass filter. So you should be able to recognize these. This is an example of another high pass filter, but it's not what we call a simple filter because it uses a number of reactances and resistances. It's a little bit more complex.
The half power frequency will change now.
Yes, we couldn't calculate that very easily. It would be more difficult.
But can we say it's cut off?
You can still calculate it, and when you do calculate, although it's more complicated.
No, I'm asking here. You said it's high pass filter.
Yes.
And the other thing that you gave us before, the
Cut-off frequency,
cut-off frequency
same as the minus 3 dB.
and the half power frequency.
They're all the same.
Also the same name.
Exactly, yes. That doesn't make any difference on the type of filter. That's any type of filter.
The difference only will be when the cut-off.
Yes.
Magically.
Here it would be more difficult to calculate what that frequency is going to be. Here it's much easier. And this is basically, if you need any calculation, you're not going to get more difficult than that. But what I'm trying to say is you can get filters which are a lot more complex, right? But you should be able to just recognize by looking at them like this would be a high-pass filter. It's just a more complicated version of this, isn't it? Like one filter after another in a sense. Now let's look at some special circuits involving inductors and capacitors. Here we just used a reactance with a resistance. Reactance with a resistance in all cases. A single reactance with a resistance. Now if we look at two reactances together, we get a different circuit altogether. Let me just erase this. Well, can you ask me that? Yeah, can you ask me that again when I talk about gain tomorrow? Remember the word gain. Both of them, yes, exactly. Both of them. You get gain in the transmitter and in the receiver if they both use directional antennas. Yes.
Can it be to use as receiver and transmitter at the same time?
You can. Yeah. In fact, that's exactly what happens on our point-to-point communication using microwaves. Transmit using the same antenna. We can use it for transmitting and receiving.
Two positions. This is the point. Two positions. Take the.
Well, what I want you to think about here is using it just for one reason, either as a transmitter or as a receiver, not both. They can actually be used for both, but if it's used as a transmitter, that's right, exactly. If it's used as a receiver, it receives the radiation from the other side, wherever that is, goes to the reflector, and that concentrates the beam onto the actual antenna, shall we say, which is here. Yeah. The principles are quite straightforward. It should give us a very narrow beam, but because it's not perfect, we are going to get side lobes. They call them side lobes. And that can affect us if ever we're involved in aligning. Now, the reason why data guys are going to be involved with this as much as radio is because our microwave link handles telephone calls and data. All right. So the telephone and data people are very much involved with that microwave link. It's them that people come to if anything goes wrong, not the radio guys. It's the data guys. So they need to be able to handle this.
Wind can affect it.
Yes, indeed. In very bad weather, bad weather has two effects on it, but wind, if you take wind, if it gets very windy, it can move. And don't forget, you don't need much movement. A small change in the position of your antenna, just a small change, and it's gone, you lose it. It's gone off to a different direction, isn't it? So if you get very windy conditions, the antenna can move a little bit. So then you've got to be able to bring it back again to get it focused again onto the...
Can you repeat what's the side loop?
The side lobe.
Why it is coming?
It's coming because we cannot have a perfect reflector. A perfect reflector would mean I can transmit from a point here to here, but this is in the space by itself with nothing connected to it. Well,
And not only that, this also would reflect something.
yes, that's right. Yes, even the point itself is going to interfere. Anything in front of that wave, anything that goes in front of that beam is going to cause small amounts of energy, if it's a transmitter, to be radiated in other directions. And that will produce a side lobe. Now, in actual practice, of course, we can't just have a point there with nothing on it. It's got to be physically connected to something. So we usually have some metal structure here to hold In the case of, for instance, a TV receiver, we call it the LMB, don't we?
Yes.
And that's right in front of your dish. So you're going to have reflections off this
There's some problem, you said
structure.
when the size of the dish bigger,
Hmm.
the focus is the signals will
Yes, we get a narrower.
narrow focus.
Yeah.
Stronger for
The
signal,
smaller the dish, the wider will be the.
stronger. Signal be stronger or only narrow?